It's a Tuesday morning. 66 million years ago, a Triceratops is drinking from a river in a place that will one day be called North Dakota. The weather is pleasant, 79 degrees Fahrenheit, clear skies, no storms, no danger signs, no tremor in the ground. Just a dinosaur, a river, and a morning that looks exactly like every other morning of the last 180 million years. But out beyond the sky, in the empty dark, something is coming that nothing here can see or feel. A rock 6 miles wide moving at 40,000 miles an hour. It has already crossed 4 billion miles of space to reach this exact point at this exact moment. In 11 minutes and 40 seconds, this river will cease to exist. The Triceratops has no idea. Neither does the T-Rex hunting nearby, nor the pterosaurs gliding above the sea, nor the small warm-blooded creatures hiding in their burrows underground. Because nothing like this has ever happened, not in 180 million years of dinosaur rule, not in the 540 million years since complex life first appeared on Earth. What is about to happen is the most precisely documented catastrophe in this planet's history. Scientists have spent decades reconstructing it hour by hour, layer by layer, fossil by fossil. A fish killed within 2 hours of impact, its gills still packed with tiny glass beads of molten rock. A thin layer of iridium, an element rare on Earth, common in asteroids, found in soil on every continent. A crater 110 miles wide and 12 miles deep, buried beneath the limestone of the Yucatan Peninsula, silent for 66 million years. This isn't speculation. This is the exact timeline of the last day of the dinosaurs. And it's worse than anything you've imagined. The world that was about to end Earth back then looked nothing like it does today. It was warmer, wetter, and more alive. Average global temperature was 14 degrees Fahrenheit higher than now. There were no ice caps at either pole. Sea levels stood 600 feet higher than they do today. North America was split in two by a vast inland sea, the Western Interior Seaway, stretching from the Arctic down to the Gulf of Mexico. Mosasaurs the length of a school bus hunted its depths, while pterosaurs with 30-foot wingspans rode the thermals above. This wasn't a dying world. It was life at its absolute peak. Dinosaurs had ruled for 180 million years, a stretch of time so vast it makes all of human history look like a footnote. They weren't struggling. They were thriving. In the Hell Creek ecosystem, the ancient landscape now fossilized across Montana and the Dakotas, the food chain was stacked from top to bottom. At the very top, Tyrannosaurus Rex, 9 tons, 40 feet long, with the most powerful bite of any land animal that has ever lived. Below it, herds of Triceratops weighing up to 12 tons each. Edmontosaurus, a hadrosaur the size of a city bus, migrating in herds of thousands. Ankylosaurus alone, armored from head to tail, swinging a bone club strong enough to break a predator's leg. And beneath all of it, hidden in burrows, were the mammals, the biggest of them no larger than a house cat. Warm-blooded, fast-breeding, mostly nocturnal, they had survived beside the dinosaurs for 100 million years simply by staying out of the way. None of them had any idea that within 24 hours this world would belong to them. The rock that changed everything. The asteroid had formed 4.5 billion years ago, in the earliest, most violent years of the solar system. An ancient, carbon-rich rock, laced with water ice, 6 miles across, wide enough to stretch from one end of a major city to the other. For billions of years it orbited quietly in the asteroid belt, until a gravitational nudge sent it drifting inward, crossing the paths of Mars and Earth. Now, on this morning, that drift is about to end. Traveling at 40,000 miles an hour, 50 times faster than a rifle bullet, it is 11 minutes from the surface. The Triceratops lowers its head and drinks. As the asteroid enters the atmosphere, the air in front of it compresses so violently it heats to 50,000 degrees Fahrenheit, 3 times hotter than the surface of the sun. The rock begins vaporizing before it even reaches the ground. Anyone standing 900 miles away and looking toward the impact site would have been blinded by the flash before the sound ever reached them, and dead before they understood what they'd seen. It strikes the shallow, sulfur-rich waters off the Yucatan Peninsula, the worst possible place it could have landed. Deep ocean would have absorbed much of the blow. Solid granite would have released far less sulfur. Instead, it hits a thin shelf of chemical accelerant. The energy released in the first second alone equals 10 billion Hiroshima-sized bombs detonating at once. A crater begins to form, eventually 110 miles wide, 12 miles deep. The bedrock doesn't shatter, it flows like liquid, throwing up mountains taller than the Himalayas before collapsing back on itself within minutes. A plume of vaporized rock and superheated steam is blasted into space at speeds over 25,000 miles an hour. Some of it will never come back, most of it will. By the river in North Dakota, the Triceratops is still alive. The first hour. 2 minutes after impact, the shockwave reaches the edge of the Yucatan, traveling through solid rock at 4 miles a second, triggering dormant volcanoes across Mexico and Central America. The ground itself begins to move like the surface of a shaken lake. 13 minutes later, that same shockwave reaches Tanis, North Dakota, 2,000 miles from the crater. We know this with extraordinary precision because of what paleontologist Robert De Palma and his team uncovered there starting in 2019. The sediment layers at Tanis recorded that day almost in real time. When the seismic wave hit, it set off a violent sloshing in a shallow inland bay, water surging back and then forward again, burying fish alive within minutes, their gills packed with the same glassy debris already raining from the sky. Those fish would lie undisturbed for 66 million years, becoming some of the most important fossils ever found. 2,000 miles to the south, the ejected debris is starting to fall back to Earth, everywhere, all at once. Each particle re-entering the atmosphere heats the air around it through friction, and the sky itself begins to glow, not in one place, but across the entire planet. In the regions nearest the impact, surface temperatures climb to 500 degrees Fahrenheit within the first hour, hot enough to set dry vegetation on fire without a spark. Forests ignite from thousands of separate points at once. Animals caught in the open die first, from radiant heat alone, the same way food cooks in an oven. Those sheltered by forest canopy survive a little longer until the canopy itself catches fire. Animals near water have the best chance. The Triceratops is still alive. The tremors have passed, but to the south, the sky glows like a forge, and the air keeps getting warmer. Underground, the small mammals are trembling but alive, with no understanding of what's happening above them, only the sense that something has gone terribly wrong. In the ocean, fish and marine reptiles are shielded from the heat by the water above them. But the ocean itself is already changing, sulfur and carbon dissolving into the surface water, its pH beginning to drop. The acidification will take thousands of years to fully unfold. It has already begun, Tsunamis and darkness. The impact displaced an almost unimaginable volume of water, leaving a hole in the ocean 110 miles wide, surrounded by walls of water hundreds of feet tall that come crashing back inward, rebounding upward into wave after wave. In the Gulf of Mexico, the first wave rises over a mile high, taller than any mountain east of the Rockies, reaching the future coastlines of Texas, Louisiana, and Florida within 2 hours, carrying a layer of debris still found in the rock record today. Crossing the Atlantic, the wave reaches the shores of what will become Spain and Morocco within 12 hours. But the tsunamis aren't the deadliest thing happening. Beneath the impact site sat a formation of sulfur-rich rock. In the first seconds, roughly 100 billion tons of sulfur vaporized straight into the upper atmosphere, where it will combine with water vapor to form a global veil of sulfuric acid, an effect that will last decades. For now, though, 2 hours in, the immediate crisis is fire. Across North America, roughly 70% of forests are burning. The sky is no longer blue. It's a black, churning ceiling of smoke stretching from horizon to horizon. Below it, survivors wait in rivers and coastal waters, not knowing they're the lucky ones, because there are no lucky ones. Not really. A full day has now passed. Fires still burn across 4 continents. But the real killer isn't the smoke. It's the sulfuric acid aerosol layer already spreading through the stratosphere, blocking more than 80% of incoming sunlight. By the second day, most of the planet's sky no longer looks like a sky, just a flat, grey ceiling letting through a dim, reddish twilight, even at noon. Photosynthesis begins to fail. Without sunlight, plants cannot make energy. Without plants, herbivores starve. Without herbivores, carnivores follow. The 180-million-year-old food chain begins collapsing from the bottom up. A Triceratops needs hundreds of pounds of vegetation daily to sustain its 12-ton body, and that supply is vanishing. The T-Rex, able to go weeks without food and scavenge what it can, feels the pressure last. But it cannot go on forever. Nothing can. The Triceratops is still alive, standing in shallow water that spared her the worst of the heat. The air tastes strange and acidic, the sky a colour she's never seen. She won't be alive much longer. 2 years of winter. 2 years after impact, the sun has effectively vanished, not literally, but the veil of soot and acid aerosols now blocks more than 80% of its energy. Global average temperature has dropped 47 degrees Fahrenheit from before the impact. Deep inland, far from the ocean's moderating effect, the drop reaches 65 degrees Fahrenheit. Rivers freeze. Soil that was once warm is now solid ice. Whatever plants survived the fires and the darkness now die in the cold. Only ferns, whose spores can lie dormant in soil for years, begin to return first, briefly covering the landscape almost alone, a grey, ashen world lit only by pale green. In the oceans, cold surface water disrupts circulation currents. Continuing acidification dissolves the shells of foraminifera, the tiny organisms at the base of the entire marine food web, and everything depending on them, down to the great mosasaurs, begins to starve. Roughly 75% of all species on Earth will not survive this winter. Every non-avian dinosaur, every lineage that ruled for 180 million years, is gone, not in one moment, but gradually, population by population, across 2 years of cold and hunger. The last T-Rex doesn't die by violence, it starves alone in a world that no longer has enough food left for something its size, but something survives. A new morning, the sky turns blue again. It takes 300,000 years. Sulfur aerosols slowly settling out of the stratosphere, soot washed away by rain, the carbon cycle painfully rebalancing itself. The great inland sea is gone. Sea levels have dropped as new ice locks water at the poles. New rivers cut through landscapes that no longer resemble the world before. Ferns give way to flowering plants, spreading rapidly into the empty, ecological space left behind. There are no dinosaurs left, not one. For the first time in 180 million years, the land belongs to something else. The mammals emerge from their burrows into a world with no predators larger than themselves. Still small, but breeding and diversifying at astonishing speed, they begin filling every available niche. Within 10 million years, every major group of modern mammals will have appeared. Whales will return to the sea, bats will take to the air. Primates will begin climbing trees in what will one day be called Africa. And 66 million years from that moment, one lineage of those primates will learn to read the layers of a rock and reconstruct, in exact detail, the sequence of events that made its own existence possible. That's not a metaphor. The carbon in your body was forged in stars that died before the sun existed. The calcium in your bones passed through the bodies of marine creatures in oceans that no longer exist. And you are here at all because on a Tuesday morning, 66 million years ago, a 6-mile-wide rock arrived from beyond the solar system and ended a world. The crater is still there, buried beneath limestone, silent. The fish at Tanis are still there, preserved exactly as they died. And the story they tell of catastrophe that became a beginning is the story of every living thing on Earth today, including you. In 2022, NASA's DART spacecraft deliberately slammed into an asteroid called Dimorphos at 14,000 miles an hour and successfully altered its orbit, the first time a civilization proved it could redirect a space rock. The dinosaurs had no warning and no technology. We have both. Right now, NASA's Planetary Defense Coordination Office tracks over 2,000 near-Earth objects, large enough to cause serious damage if they struck. None are currently on a collision course, but the same gravitational forces that sent the Chicxulub impactor toward Earth 66 million years ago are still at work today. The real question isn't whether another large asteroid will eventually cross our path, it's whether we'll see it coming in time. The second lesson is about the speed of ecological collapse. A 180 million year old food chain began failing within days, not because the asteroid destroyed it directly, but because it cut off the energy source holding it all together: sunlight. Climate scientists studying that impact winter use the exact same physical models today to simulate what a large-scale nuclear exchange would do to Earth's climate. The mechanism is identical, only the timescale differs. And the third lesson, maybe the most important, the animals that survived weren't the strongest, the largest, or the most dominant. They were the ones that could adapt fastest to a world that had changed overnight. Small size, flexible diet, the ability to get by on very little, and the ability to reproduce quickly enough to generate new variation under pressure. Those same traits carried life through the darkness 66 million years ago, and they're the same traits that have carried every lineage since, including ours, through every smaller catastrophe that followed. Resilience was never about being the biggest thing in the room. The fossil record has proven that over and over. We began this story on a Tuesday morning, a Triceratops at a river, a clear sky, a world that had looked the same for longer than the human mind can really grasp. That world is gone. Every animal on those floodplains, every creature in that inland sea, every pterosaur riding those thermals, gone within 2 years of a single Tuesday morning. But here's what didn't go. The river is still there, a different river, but the same water cycle that has been running for 4.5 billion years. The sky is still there, still blue, still governed by the same chemistry that existed long before the first dinosaur ever drew breath. And life is still there, diminished, transformed, unrecognizable from what it once was, but still here, still finding a way. When Robert De Palma held that fossilized fish in his hands in 2019, he understood, in the most immediate way possible, what it meant. A creature that died on the worst day in the history of vertebrate life on Earth, whose death, 66 million years later, was helping the descendants of the survivors understand exactly what had happened to them. There's something in that which goes beyond science. The asteroid didn't get the last word. Life did. It always does.